2 minutes. 2 minutes. No, wasn't planning on.
At least from our research, are we supposed to determine like if the flow rate or the pressure is like Bode or is it just constant? I'm assuming it's full screw. It's a harder.
That's a good question.
So like
for testing, just use a flat rate.
Just use a flat rate? Yeah. Because I'm like, even if we can model the curve with like differentials, I think still I don't know how to do that.
Yeah, for analysis, just use a simple flow.
Okay.
All right, guys, it's 12:30. Let's get started. Lord, thank you for bringing us together this afternoon. Thank you for everything you do for us. I pray that you would help us to make it through the next few weeks, to get everything done that we need to be successful. In your name we pray. Amen. All right. Still haven't finished grading the exams yet. They'll get done at some point. Eventually. Some point eventually. In the future. Hopefully by Saturday. Otherwise, it will ruin my weekend. But whatever. It's not your problem. That's my problem. Okay. So what we're doing today, we're going to recap and we're going to do Bode diagrams. Right? We're going to talk a lot about them. We probably won't get through everything that I have here today, and that's fine. But we'll get through most of it. Okay, so what have we been talking about? Well, according to this, nobody filled it out. So another perfect class. Chalk one up. Or, don't even need to recap, really. But just, let's just say that we were going to recap. Anyway, we talked about how to find the steady state response of a system due to a sinusoidal input, right? And there was this one equation that came up like 3 times in a row with boxes, so it must be important. And in fact, I said that it was very important, and I said that you needed to know how to use it, and that was the y steady state equation, where y steady state is equal to the magnitude of the sinusoidal transfer function, g of j omega, times the initial amplitude times the sine function, omega t, plus phi, where phi is my phase shift, which is calculated by finding the argument of g of j omega, which is just, the tan inverse of the numerator divided or minus the tan inverse of the denominator. And we went through the whole derivation of everything, right? And how to find g of j omega and all of that. Do you guys have any questions regarding last class at all? No, nothing. Okay. Well, in that case, these are the things that are due, right? Don't forget to turn them in, right? Lab 3, mega homework, exam 3, benchmark, and your presentation, right? So lab due on Sunday, homework due the following Sunday, exam due on the last day of class. And when I say due, I mean I'll do it on like how we have been. Use the test mods again. I think that works pretty well. And then your benchmark assignment due on the very last day of the semester, which is the 20th. Your presentation due on the same day. Then you guys get 5 days off, and then we have to start the next semester, right? That's pretty sure that's how it works. It's more than 5 days. It's like 2 weeks. But all right, cool. By my calculations, that gives us today, including today, 4 more classes that have content associated with them. All right, 4 more classes where there's actually lectures, 1 of an exam. So almost there, almost there. So let's do a problem. Let's do a little warm up here, right? Consider a mass being subjected to a sinusoidal force input. Right? The mass has a mass of 0.2 kilograms. The damping constant B is 1 Newton second per meter. We want to create a model for the above system in terms of the velocity of the mass. And we want to apply the prescribed input force and determine the total response when omega is equal to 15 meters per second, but also when omega is equal to 60 radians per second. I don't want to say meters per second before, they're both radians per second. All right, so I want to analyze this system at 2 different input frequencies, and I want to compare those results, right? I want to plot the input and the response for each case by hand. I just want to do a quick sketch, make sure I'm understanding what's going on, and then I also want to check it using simulation, right? So that's the plan here. What does this system look like? Okay, good question. I'll draw a schematic, right? Here's a mass on the ground. There's some force, F of t. And there's some viscous friction. That's my schematic. Okay. So what is this in the real world? Is this a real thing? Sure. It's a small part that's been lubricated and sliding on some surface. It's a thin film problem, right? There's no spring, right? So how do we start this? Right? Well, we're specifically asked to find the model, right? So I guess we would start with a free body diagram, write down our inputs and outputs, do our mathematical truths, and then reduce it till we get our input-output equation, right? So let's do that stuff. Right? Also, I'm just going to point this out right now. F of t is equal to sine omega t, just a simple sine wave. Right. Right. And we're given an initial condition of 0. Right. So free body diagram. Right. Beautiful. There it is. The 2 forces, right? I've got my applied force and I've got my damping. Okay. What's my input? Yep. F of t. What's my output? W. X. Velocity. All right, we're told that we want it specifically in terms of the velocity. We want to find the output velocity here. Right? Now this should look like a familiar model, right? Because we've done it a bunch of times in the rotational space, right? We've done this a bunch of times in the rotational space, where we have some rotating inertia that has a damping but no stiffness. This is the same thing, but it's the translational variant of that, right? So what are my truths? Somebody hit me with a mathematical truth. Someone from home. Let's go. It's your guys' turn.
Sum of the forces equals mx doubled up.
Yes. That's an excellent one. But Chris, I'm going to write it in terms of velocity since we have output velocity. But good. Very good.
Would F be equal to M? Yeah, whatever that. What's that letter again? I'm sorry. It's just not dotted.
That's a V. For velocity.
Yeah, so MV.
So F of B is equal to MV. Does that look right? Yeah. It's B. Right, the damping coefficient.
My bad.
That's all right. That's it, right, for this. So, I mean, if we really wanted to in our truths, right, we could write that, M was 0.2 kilograms and B was equal to 1 Newton second per meter, and F of T was equal to sine omega T, right? But that's not really going to help us in our reduction, right? That's just to have it there, and to have our knowns there, but that's really going to help our reduction. And we can do this. We can sum our forces. We're going to have F of T minus F of B. F sub B is equal to mv dot, or, mv dot plus bv is equal to F of T. Okay. And we're asked to find the frequency response, right? So that's another fancy way of saying the steady state response to a sinusoidal. Okay. So we're asked to find the frequency response. We're asked to find the frequency response. If we're asked to find the frequency response, we need to have the sinusoidal transfer function, right? That is what we need. And the first step in getting the sinusoidal transfer function is to find the actual transfer function. So what is the transfer function for this? What's the first step in finding a transfer function? Laplace transform. So what's the Laplace transform of this? If you're going to take the Laplace transform of this, right, with zero initial conditions, right? Because that's the big part for a transfer function. Right, Trevor? Yeah, you can use Y and U if you want. If that's your deal. I prefer to not use Y and U. And the reason that I don't is because I feel like you lose sight of what your input and your output are, right? For me, I like having V there because I know that I'm solving for a velocity. But if you wanted to use Y and U, then that's fine too, right? Because that's how the book does it, and it lines up with the whole notation that the book uses. Okay? So yeah, we find our Laplace transform, but now we want the transfer function, right? So what is a transfer function? It's the relationship, the ratio of my input or my output to my input, right? Which is G of S, which in this case is 1 over ms plus B. 1 over ms plus B. So there's my transfer. All right, so far so good. We're cool. Maybe everybody's tracking. Any questions? So we have the transfer function. We need the sinusoidal transfer function, right? So I'm going to rewrite my transfer function up here so we have it. 1 over ms plus b, which is the same as 1 over 0.2s plus 1, because I didn't just plug in m and b at this point. And if I want the sinusoidal transfer function, right, I want g of j omega. So it's, remember, it's as simple as me plugging in j omega every place that I see an s. And I'm going to switch the order here for a second. Doesn't matter. Right? J omega and omega j, same difference. And that's great. And I'm going to leave that as is for right now. We'll talk about it in a second. Because why? What are we trying to do? Remember, for our particular equation, right, we've got VSS, steady state velocity, has to be equal to G of j omega times the initial amplitude times the sine of omega t plus b. How do we find the magnitude of G of j omega? Well, we have to find the magnitude of our sinusoidal transfer function. How do we find phi? That's the argument, right? And then we're going to step through this. But remember, we are trying to build for a steady state response to a sinusoidal input. This is what we are trying to build. This is what we're trying to do. Okay. So we were given two conditions, right? Omega equal to 15 radians per second. So what do we do? Well, that just is telling me that I want the magnitude of G of 15J. So anytime I have my transfer function here, I'm going to take the magnitude of this transfer function where omega is now equal to 15 radians per second, right? And if I do that, my numerator is 1 squared plus 0 squared, right? Remember, it is the Pythagorean theorem to get the magnitude of the numerator divided by the magnitude of the denominator, which in this case is the real portion, 1 squared, plus 0.2 times 15 squared, square root. Well, what is that? You crunch those numbers, what do you get? What was that, Christian? 0.316. Nailed it. There it is. Right, 0.316. So that's our magnitude, right? 0.316. This is going to end up going into that first part of our equation, right? We're going to hold it for a second. Let's find the angle, right? Phi. So I need to take the tan inverse of the top, right? Tan inverse of my top, which would be the imaginary divided by the real, which is 0/1, plus the tan inverse, oh, sorry, not plus, minus. Why is it minus? Remember, we went over this last class. Because of the polar form, you have e to the j phi 1 over e to the j phi 2. And so when you combine two exponents, you subtract them, right, by division. The imaginary portion here is 0.2 times 15 divided by 1. We can crunch those. This one's negative 1.25 radians. Remember, when you're doing the calcs for this, you want to be in radians on your calculator. Or at least if you're in degrees, then convert it to radians, right? Times pi over 180. Or you can get crazy, times 2 pi over 360. That's the stuff, man. Right, so now that we have those, I can say that my VSS for my 15, for omega is equal to 15 radians per second. Well, I don't even need to put that in there, right? So my VSS has to equal 0.316. Well, U of 0 was just 1, right? Because my initial input was just sine omega t times sine of 15t plus negative, so minus 1.25. There's the steady state response for my velocity at 15 radians per second, right? And now we're going to rinse and repeat, and we're going to do the same thing at 60 radians per second. I'm going to rinse, repeat, do the same thing at 60. We good so far? Anybody got any questions? No? Everybody's cool? All right, we find the magnitude, we find the phase, we plug it into our equation, and that's that. Okay? So let's do it again. This time omega is equal to 60 radians per second. So we need G of 60J, which is going to have the same numerator, right? Because we didn't change the numerator at all. Gives me this. All right, so what's my magnitude? 0.083. What's my phase? What do you get for phase? What's that? Yep. -1.4. Great. So VSS is equal to 0.083 sine of 60t minus 1.49. There we go. Why is u naught 0? Well, we were given sine of omega t, right? So u naught is 0. Or u naught is 1. I don't know why I said 0. It makes no sense. If it was 0, the whole thing would be nothing, right? You just apply an input of 0 to something, then the output should be 0. Okay. So now we have to draw it, right? Because it said to draw it, so we should draw it. Well, technically, I guess it did say to plot it, right? It didn't say to draw it. I'm going to do it by hand because I don't have a really good way of plotting it on here to show you guys. So be prepared to marvel at these drawings. They're going to be quite something. They're going to set the internet ablaze. All right. So what do we got? So I'm going to draw it by hand and then we're going to check it. So if you were going to do this, right? If on homework it said to plot it, you should do it by hand. That's what it means to plot it. You're not trying to get something accurate. You're just trying to get an idea of what this looks like and how it compares to the input. It's a sine wave, so it will repeat forever. So just do one period. All right, just do one period. Okay. So what do we have, right? Well, first of all, we have f of t is equal to sine of 15t, right? And that is accompanied by VSS is equal to 0.316 sine of 15t minus 1.25, right? And we also had f of t is equal to sine of 60t, which is accompanied by VSS is equal to 0.083 sine of 60t minus 1.4. Right? Those are the four things that we have here. So we're going to start on the left-hand side here. We're going to draw the 15 radian per second input and the 15 radian per second response. Nope, not that one. Time in seconds, velocity in meters per second. That's 0. Negative 1, 0.8, 0.6, negative 0.4, 0.22, 0.8, 6, 2. Perfect. Right. So we plot sine 15t. You can do this on your calculator if you have a graphing calculator. Right? Sine of 15t is going to give me a peak at roughly 0.1 seconds. And then again, around 0.3 seconds. And it'll cross 0 about here and about there. So right, so like I said, marvel in all of this hand-drawn sine wave in all of its glory. There's an amplitude of 1 and a frequency of 15 radians per second. So Dr. D claims. How would you plot this if you really wanted to? Go into Excel, right? You would put the equation in and you'd vary time from 0 up until whenever you wanted, and then you would plot it that way, right? That would be a good way to do it. If you have a graphing calculator, you just pop that function in and plot it, right? You're good to go. Okay. What about the red line, right? The steady state velocity at 15 radians per second. All right, so if we plug in 0 for t, because we want to know where this starts, what do we end up with, right? Well, we end up with the 0.316 times the sine of negative 1.25, right? Turns out, excuse me, that is roughly 0.3. It's like right over here. So at t equals 0, right? Just plug in 0. Excuse me. I know that my maximum amplitude has to be what? Well, it has to be 0.316, right? So when does that happen? That happens when the term inside of the sine equals 0. When does that happen? That happens a bunch, right? But we can solve it a couple of times here, and we can say that the first time that happens is when 15t minus 1.25 is equal to 0. So whatever number that comes out to be, and it turns out that that's going to be around 0.2-ish. This will have a peak about here. The next time, right? So we can also figure out 0 crossings. And we can also figure out 0 crossings. This crosses 0. Well, this crosses 0 at about 0.5-ish. Comes up, comes back down, crosses 0 again right before 0.3. Has a peak around 0.4. And then pops back up. Right? So something to that effect. Yeah. So how is this different than the one that we drew in black? How is this changed from its input sine wave? Yes, Trevor, it is shifted and shrunk. Exactly. Right? Shift and shrink. So yeah, it's exactly what happened, right? You have this phase shift and you have this scaling of the amplitude, right? Okay, so what about this sine of 60t? How would you expect that to look when compared to sine of 15t? What does that know? Is the amplitude different? So what does changing the frequency change in terms of the plot? All right, it brings everything closer together, right? You're gonna have 4 times as many peaks as you have for sine of 15t, right? It's gonna make it more frequent, hence why the frequency, right? It's more frequent. So we can draw that. It's gonna look basically the same. It's just gonna be multiplied, right? So I'm gonna try my best here. So something to that effect. It's not the best, right? But it gives you the general idea, which is what we're trying to do. Again, if you were going to plot this, I would wholeheartedly recommend doing this on Excel or even in MATLAB, right? Define your time vector, run it in MATLAB. That's the input. That's the other input.
Oh, sorry.
Yeah. All right, so now we'll do the steady state output for this input. So you would expect, again, that you would have a shift and a shrink, right? Because what this is telling us, what this equation tells us, right? What the red and the blue equations tell us are this. In the case of 15 radians per second, we have scaled our amplitude by 31.6%. So we have lost roughly 70% of our amplitude from the original. The next one tells us that we've lost roughly 92% of our amplitude from the original. So it's going to shrink quite significantly, right? And in fact, after we calculate our shift, which gives us a starting point of roughly right here, we're going to be something like that. All right? So this is a big idea, kind of, because we didn't do anything except change the frequency that we're operating at. We got two very distinctly different outputs, right? And this is where the idea behind Bode plots comes in. Because a Bode plot takes this generalized form of our magnitude and our phase equations and sweeps it through the whole range of frequencies and allows us to see how changing the frequency of our input affects the magnitude and the phase of our system. Now, I haven't really talked about with you guys why that's important. We'll get into that in a little bit today. Okay. And much more next week, right, when we start talking about vibration, isolation, and things of that nature. All right, so I owe you a Simulink, right? Because we got to check this versus Simulink. I mean, you can't not check it versus Simulink. There we go. Cool. That'll do. Okay, so allow me to share this. Here's a Simulink model. Please don't crash on me. Okay. It's my Simulink model. Notice I've got my transfer function, right? I've got my sine inputs. This one's my 1 at 15, right? This guy is 1 at 60. I will run this. And share this scope. And then crash the whole thing. Nobody can see that though. Right, so Now everybody can see it. It's great. Good stuff. So the yellow line is my input, the blue line is my output. Okay. And look, it looks somewhat like what we drew. There's some funky stuff happening in the beginning, right? That has to do with the transient response, which we weren't plotting. We were only plotting the steady state response. So remember, when you start up, there is still some transients in the system, right? There's some effect due to your natural frequency. And at the beginning, you're going to have essentially two sets of vibrations that are occurring, right? One at omega n and one at omega. And when both of these, eventually the natural frequency dies out because it's held by this exponential term, right? And we're just left with the output. Okay. What about the other one? Right? What about the other one? Same deal, right? It's like an optical illusion, right? It looks like it's there, but it's not there. So yeah, right, same deal. Just happens faster. By faster, I mean more frequent. And it has a frequency of 60 radians per second, but it also really diminishes the size of this oscillation.
I have a question.
Yes.
In the sine wave source, did you put in the phase as well, or just the frequency?
No, Chris. So you don't put the phase in to the source because the source was defined as just sine omega t.
Oh, that's right. Okay, yeah. Thanks.
Really, the only time that you use that phase portion for, well, in this class, the only time we'll use that is if we want a cosine input instead of a sine input, because you have to phase shift by 90 degrees. You guys have any other questions on this, right? The general process is what? The general process is make the model, find the steady state response, plot the steady state response, compare it to Simulink or some other source, right? That's the general. Typically Simulink, right? Typically. Okay. Well, if there's no questions, then we're going to do time trials today for points. You'll get 45 minutes to do the next problem. Okay. What problem? This one. You guys know the rules and the deal, right? We're going to do this. What are we going to do? We're going to find the model, and we're going to find the steady state response, and you're going to draw the input and the steady state response, and you're going to create a Simulink model to make sure that it's what you thought it was. Okay? I will send you to your breakout rooms. All right, you guys get 45 minutes. I'll bounce around and let you know. Oh. Nice. All right, we back? We're back. All right. All right. All right. Good stuff. Everybody did pretty well. Got most of the way through it at the very least. There's one thing that we're going to talk about, right? There was one trick here, and if you didn't, right, there's always a trick, right? Dr. D's always trying to trick us. You know, all that. It's true all the time. All right, anyway, how do we do this, right? Well, we have to find a model, same way we do every model, right? We do our thing. And yes, this if at this point in the semester, after 13 weeks, you feel like this is Groundhog Day because we keep solving the same equation over and over and over. Yeah, that's exactly, we just keep solving the same ones over and over again, right? You basically are solving the second order system equation forever, for your whole life. This is what you signed up for, okay, as engineers, really. I should probably, unfreeze the classroom computer. That'd probably be good too. So here we are, right? And everybody's work that I've seen, you guys all made the model correctly, right? You all took the Laplace transform correctly, and we all got to the Laplace, to the transfer function, which I thought I had written down. There it is. It got skipped. It's fine. We got it. All right, so I got this now. Fantastic. So once we get here, what do we do? Well, this is just G of S. So we have to plug in J omega for S, right? And all we do is we just plug it in directly wherever we see S, because we went through the derivation, but that's how we do it. That's how we handle it. Great. Now this is the trick, right? This is the trick point. And if you didn't figure it out, we talked about it. And if you figured it out, that's awesome too. But when you square this, right, remember J is equal to the square root of -1. And you probably can't see it, but I have it written here on this window because I need 45 minutes to do a bunch of stuff. And that was one of the things I chose to do while you guys are doing this problem. So it's worth. All right. So what happens if I square this? What do I get? -1. And if I cubed this, that would be just J times J times J, or -1 times J, which is just -J. And if I took the fourth power, right, this would just be 1. And this just goes on in a cycle forever and ever and ever, however many ordered system we have, right? And so every even power takes the imaginary number and shifts it into the real, right? And every odd number, odd power, keeps it imaginary. So how is this helpful? Well, because this now becomes -0.2 times omega squared plus 1.6 j omega plus 65. And if I plug in 18 here, turns out that 0.2 times 18 squared is 64.8. Turns out. That one worked out pretty well. So we get 65 minus 64.8. That's my real portion. Plus 1.6 times 18, not omega, but j. J. Right, and if I crunch these numbers, right? Well, I'm not crunching any numbers here, right? If I want the magnitude of G of 18J, right? Well, this is just 0.2 squared plus 1.6 times 18 squared square roots, which gives me 0.035. Okay. So the trick was the J squared. And what? Guess what? Now we've seen it, so we won't be tricked anymore, right? Is it important to recognize that? Yes. Why? Well, I think we've established that most real-life systems are second order if you're talking about mechanical systems, at minimum. Right? At minimum. If you have some systems right? Electrical systems in particular can get high order very, very, very quickly, right? And this is applicable for electrical systems as well. We'll do a couple examples like that. So we have to find the phase now, right? So let's find the phase. Phase is going to say, is going to be phi is equal to the tan inverse of 0 over 1 minus the tan inverse of 1.6 times 18 over 0.2. It gives me negative 1.56 radians. So my steady state variable, my steady state becomes g of j omega times u naught sine of omega t plus phi, or 0.035 times 1.5 sine of 18 t minus 1.56, or 0.0525 sine 18 t minus 1.56. Not AT&T, but 18t. Right? That's a dumb joke. Why would you say that? I don't know. Why do I say half the things that I say? I don't know. Because I'm the one on YouTube. That's why. Okay, I say what I want. Because everybody knows that YouTube is a platform for making dumb jokes. That's what it is. Nothing useful has ever come out of YouTube. It's not true. Okay. We have any questions on how to find the steady state response? Everybody who ran through the problem got at least this far, or is at least about to get done with this, right? The next part is to put it in Simulink, right? And you can plot it, right? You know it's going to be a sine wave and then a smaller sine wave that's shifted. That's what we're expecting. But if we throw this into Simulink, we get this. Right, so make it in Simulink the way that you think you make it in Simulink, right? You have the transfer function, you put the transfer function in, you know what the sine wave input is, you throw a sine wave input into it, and then you pop it out to a scope. Right, that's where we're at. That's what we do. Okay. We have any questions? Right. If you really wanted to draw it, right, you could. I'm not going to take the. I don't think it's value added. I think we can draw sine waves. Yeah. Especially if you're given the equation, right? If you're given the equation and you're told on a homework to plot the sine wave, you know, I don't think it's unreasonable that you'd be able to plot the sine wave at this point in your college career. Good. Any questions? No.
Instead of like with the differential integration function, like it kind of shows the change from the beginning sine wave and steady state, like
Right. So the question is, in time domain, right, we were concerned with characterizing the transient response, right? Figuring out how long it takes, what does this look like? Is it damped, underdamped? What's my maximum overshoot? All of that. This is you're correct, Trevor. We're just mostly concerned about steady state. And the reason being that sinusoidal inputs, right, are very common in machinery and systems that run for long periods of time at steady state. So it becomes a fatigue loading issue, right? And that's where we're kind of, I won't say that we're headed there with our analyses, but we're trying to understand if we have these vibrational inputs, is there something that we can do to attenuate those vibrations and cause less of an issue, right? And attenuate's the big word for the day, right? And attenuate, it just means to lessen, right? We're lessening the amplitude of our vibrations. It's the opposite of amplification. All right. Any other questions? No? We're doing all right. All right. Well, in that case, we are going to discuss Bode diagrams. Okay. What time is it? Perfect. So the previous discussion and examples illustrate how frequency can be easily computed if we know the amplitude ratio and the phase angle, right? That's basically the whole point of the last three examples that we did in class, right? The two today and the one last class. If we can calculate magnitude and phase, we can calculate the frequency response, right? That is what we need to do. You hear frequency response, you should automatically say, I need to get the magnitude and the phase of this, right? That is where our brain goes. So we can create two plots of these quantities, right? Magnitude and phase of a sinusoidal transfer function versus the range of input frequency, right? And I talked about this a little bit in that first example, right? The reason that we wanted to plot two different frequencies is to see what is the effect on the system, right? How does that affect my output? Both of these plots together are a Bode diagram, right? The magnitude and the phase. And I believe that you guys have at least seen Bode plots before, if not discussed them, right? So have we all seen Bode plots before at some point, or is this like? Okay. Okay. So you at least know that they exist. That's important, right? They were named after H.W. Bode Bell. H.W. Bode, who worked at Bell Labs. A lot of modern control theory, we say modern control theory, when we say modern control theory, comes out of Bell Labs in the 1930s. That is what is considered modern control theory for the most part. Okay. A lot of the diagrams that you may have heard of, if not used, like a Nyquist diagram, Nyquist frequency, those are all Bell Labs things. Bell Labs did work. They did work, man. The amplitude ratio, all right, so I'll go back for a second. The amplitude ratio is traditionally plotted in decibels. When we talk about it on a magnitude plot, on the Bode magnitude plot, everything is going to be in decibels. How do we get from what we calculated to decibels? Great question. Well, you use this equation. And we will watch a video on Tuesday that kind of goes through the history of the development of Bode plots, which I think is an interesting video. You guys can, I guess, be the judge of that. But anyway, 20 times log. Remember, that's log base 10, not natural log. We use natural log to calculate this. You'd be very sad. Right, so what are we doing, right? We're going to take that magnitude that we found, and we're going to multiply it by 20. Well, we're going to take the log of it and multiply it by 20. And that gets us our decibels. How many decibels of magnitude do we have? Okay. Here's some things about dB. 20 log of 1 is equal to 0 dB. So if you read, remember what we're looking at here, right? Amplitude ratio is how much am I scaling my sine wave by, right? How much am I scaling my sine wave by? if you have an amplitude ratio of 1, you are not scaling it at all. So you have no magnitude. You're not gaining anything, but you're also not losing anything. So this is equal to 0 dB. Any magnitude that's greater than 0 correlates to an amplitude ratio that's larger than 1. So if you have a magnitude that is larger than 0 dB, you are applying amplification to your system, right? Because you will get out a larger sine wave than what you put in. If you have a magnitude in dB that's less than 0, this correlates to an amplitude ratio of less than 1. Now, the amplitude ratio will be between 0 and 1, right? Well, that's not true. It will be between 0 and something. It will never be negative, right? But it can't ever be, right? So let's put it this way. If you had an amplitude that's a decimal between 0 and 1, it's going to be a negative dB. Anything larger than 1 is going to be positive dB. And anything correlating to a negative decibel level, a negative magnitude, indicates that we are attenuating our signal, right? So we are reducing it. Very small amplitude ratios equal very large negative dB magnitudes. Okay, so here's a quick example, right? If you were given a gain or you found a gain or a magnitude of this, 0.124, what is this in dB? What is it? Negative 21.7. Do we agree? Do we disagree? If you don't know where log is on your calculator, it might be like mine. Mine doesn't have a log button, right? But it's hidden inside the math function. You can dig for it. Or if you have an alphanumeric calculator that lets you type, just type log, open parentheses, put your value in, close parentheses, hit enter, get log out. And so the log of 0.124. Confirmed. It is negative 18.13 dB. All right, this says negative 18.13. I got PowerPointed Microsoft. Anyway, I just got demonetized. I can hear it happening. Okay, so yeah, so why do we want it in decibel? Reasons. It has to do with controls, right? It's a lot nicer and cleaner to plot it as dB instead of a number between. I think it makes more sense when looking at the plot that when you see a negative number, you are reducing the amount of signal that you have, as opposed to worrying about, well, my whole plot goes from between 0 and infinity, right? And anything less than 1 is now, so it normalizes it very nicely. Okay. We can make rough sketches of Bode diagrams by applying simple rules that we're going to illustrate through a couple of examples. Right, so what we're going to talk about is how to draw a Bode diagram based on the asymptote method. Now, what you're going to draw is not the actual diagram itself. What you're going to draw is the asymptotes. You're drawing the envelope that the diagram fits inside, right? So bottom line, and I will level with you guys. The amount of times that you will ever use a hand-drawn Bode plot to do any significant analysis is 0. Okay. So why? Why do we need to know how to draw them? You need to know, you need to have a good feeling about whether your results look correct or not. You need to understand where the asymptotes are so you know whether, it's all about being able to check your results and have confidence in the analysis that you're doing. Okay. Getting a gut feeling for how Bode plots look is very helpful when you're designing systems as well. We can talk about that next class. All right, so here's my rules for asymptotes. This is for first order systems, right? We'll talk about second order systems next week. But for first order systems, you're going to have a flat, low frequency asymptote that exists with a magnitude of 20 log 10 K. What the heck, Dr. D? What is K? Where did you get that from? Okay, two things. If I have a transfer function, right? Let's just say I have some transfer function that looks like this, right? MS plus B. If I write this first order transfer function in standard form, I'll get this, K over tau S plus 1. K over tau S plus 1. K is just the DC gain, really. The system gain, it's the DC gain, it's whatever you want to call that, right? So we have a low frequency asymptote that happens at DC gain. We also have a high frequency asymptote of negative 20 decibel per decade that exists. And that starts at what we call the cutoff frequency. Right? The two asymptotes meet at the corner. Sorry, not the cutoff frequency, the corner frequency. Cutoff frequency is something else. Dr. Dean, don't go there. At the corner frequency. So called because it forms a corner. All right? Imagine for a moment, if you will, this is my one asymptote, and this is the other one. I know, it's a very technical demo. This point right here that looks like a corner, that happens at the corner frequency. This point right here at the corner. Okay. What is the corner frequency? It's 1 over the time constant. Thus ends the rules for magnitude and begins the rules for phase. So there's 3 things that we need to know to draw the magnitude asymptotes, right? You need to know the corner frequency, you need to know the DC gain of the system, or really 2 things, because if you know those 2 things, then you know how to draw a line with a slope of minus 20 dB per decade. And we'll talk about what that means in a second. What about phase? For a first order system, phase angle starts at 0 degrees for low frequencies and asymptotically approaches minus 90 at high frequencies. It crosses minus 45 at the corner frequency. Crosses minus 45 at the corner frequency. What's that, Trevor? So, all right, yeah. So, good point, right? Trevor made an offhanded comment about the use of degrees because he's a radianist, apparently. He outed himself as such. So why? So here's the deal. Bode magnitude happens in decibels. Bode phase is reported in degrees. When we do our calculations, we don't want magnitude in decibels and we don't want angle in degrees. So we're going to have to convert, right? Which is fine, right? Because why? Because you want to go from degrees to radians, right? Multiply by pi over 180 or 2 pi over 360 if you're feeling crazy. You want to go the other way, right? Multiply by 180 over pi. Okay, so those are the rules. Let's put these into action, right? With an example that we'll step through. So here's a transfer function. We're given this transfer function 6 over s plus 4, and I'm going to rewrite it in standard form, right? And the piece that we're missing here, right? The piece that we weren't given is that if we divide everything by 4, we end up with 6 times a quarter over a quarter s plus 1. Right? Just divide everything by 4. And that gets us back to where we need to go. Fantastic. If we write it in standard form, we know that tau is equal to 1/4. So we can pull off that the corner frequency is equal to 4 radians per second. And we can pull off K, right? So we know the DC gain is 1.5. So what is the sinusoidal transfer function for this then? Say that one more time, Trevor. Sorry. Yep. Substitute in j omega for us. There we go. Does it matter which version you choose? No, it doesn't. It absolutely does not matter whether you pick the standard form or the other one. They are equivalent, right? Right. Hint: replace s with j omega. Excellent. All right. So this means what? This means that the Bode diagram is simply a plot of the amplitude, magnitude of g of j omega in decibels, and the phase, which is the argument of g of j omega in degrees, versus the input frequency, and it's plotted on a log scale. Right, so we're going to use a log scale on the x-axis and not a log scale, right? So this is a semi-log plot. Okay. Magnitude and phase are both functions of what? There it is. Frequency. All right, frequency. Exclamation. Very exciting. He says, right? So here, look, this, if we wanted the magnitude of this transfer function, here it is, right? Square root of 6 squared plus 0 squared over square root of 4 squared plus omega squared. What about the phase angle, right? Well, here it is, right? These are both functions of omega. And what we are going to do is we are going essentially to plot this by changing omega, right? We'll plot both of these by changing omegas. And how are we going to plot it? We're going to go old school. And we're going to make a table. It's old school, man. Look at this. beautiful table here that I did not make, that I took from the textbook. Right? But I totally could have made this if I wanted to. I just don't want to. Right? Says proficient in Microsoft Office on my resume, so I could probably do this. Probably. Okay, so notice the input frequencies aren't super linear. They kind of jump all over the place, but that doesn't really matter. All right, so Bode plots will never start at 0 frequency, because if you're starting at 0 frequency, nothing is happening. Right? If you put 0 in there, you're going to get 0, and an input of 0 will give you an output of 0. Right? Right, so we pick some frequencies, right? And then we put our magnitude equation in the first one. We convert it to decibels in the second column, or the third column, rather. And then in the fourth column, we've already converted into degrees, right? And notice a couple of things, right? Here, we've got this DC gain. Remember, we had our K was 1.5. You know, at 0.1, we're close to 1.5, right? So we're close to our asymptote. As frequency increases, our magnitude decreases. Okay. When we get to the corner frequency of 4 radians per second, you can see we're about to transition, right? We're about to transition from amplification to attenuation. So frequency decreases in this case, or frequency increases causes, a frequency increase causes a magnitude decrease and a phase increase. Right? Adds more lag to our system. Okay. So we can take those data and we can plot them, right? So if you put this in Excel, Excel will let you do a semi-log axis, and you can plot these in Excel. Now, there's a couple of things about this that I'm going to talk about in a second about how to read it, but right, this is a standard Bode diagram and what it looks like, right? It has 2 parts. It's got the magnitude on top. Notice magnitude is in decibel, right? And degrees for phase. The x-axis is a log scale for frequency in radians per second. All right, so we had, so how do we read this, right? How do we read this? Great question. 10 to the minus 1. All right, that's 0.1. This next tick mark, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 10 to the 0, 1. The next tick mark, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 1 is 10, 20, 30, 40, no, 45, 40, 50, 60, 70, 80, 90, 100. If you want to go to 10 to the third, it'd be 100, then 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Right, so reading the Bode plot, and the thing that trips up most people, right, is remembering that this is a log scale, right? So going from 10 to the 0 to 10 to the 1 is hard to mess up, right? But if you're asked for a frequency of 11, right? This is 20. So 11 is somewhere in there. Okay, so keep that in mind. What do our asymptotes look like, right? Because we made a big deal about making rules about asymptotes here, right? So we have K was 1.5. What's 1.5 in decibels? What's 20 log of 1.5? Somebody Somebody run that number really quick, please. 3.52. That's, let's say that's like here somewhere. This is my low frequency asymptote, right? I have a flat low frequency asymptote at K, in dB, right? My cutoff frequency, I'm sorry, my corner frequency, I got to stop that, was 4 radians per second. So that's 1, 2, 3, 4. This is 4 radians per second right here. And at this point, I am going to lose 20 dB per decade. So every 10 ticks, I will lose 20 decibels, right? So start up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I should be down about 20. So what's that? That's 3. Yeah, sure, like right there. And so it's more like this sort of line here. There's my asymptotes for magnitude. Notice it is the envelope inside which my Bode diagram fits, right? It is nice, this nice asymptotic envelope. Okay. So when we are drawing these by hand, we are not trying to draw the line, we're trying to draw the asymptotes. We're trying to get a general idea of where this is going to fit and a general idea of what sort of attenuation we can get at higher frequencies. Okay. What about this, right? Well, what about this phase? Let's mark this here. Right, that's my corner. It's my corner frequency. I'm going to start with an asymptote at 0, and I'm going to finish at minus 90, right? And at the corner frequency, I will cross minus 45. So at the corner frequency, you actually shift which side your asymptote of the asymptote your plot is on. Right? So that makes sense. That's what the asymptote look like. You can kind of tell that with the phase, it's much more, drawing the asymptote gets you much closer to what the actual value is, right? What controls the slope of the phase asymptote? Well, it depends on your time constant, right? Smaller time constants are going to have a faster dip in phase, right? Because if I move closer to 0.1 here, that line has to have a sharper decrease to get to negative 45 quicker, right? Okay. You guys have any, well, so here it is again, right? Just the same stuff, but drawn a little bit nicer. Again, showing off my proficiency in Microsoft Office. I know I shouldn't brag about it, but you know, it took me a while to get there. Anyway, so right, same deal. We've got this flat asymptote to start with at the corner frequency, or sometimes called the break frequency. We start our minus 20 dB per decade. This is a lot nicer because you can definitely tell that we're losing about 20 dB per decade here, right? We started here. And if you take a look at this point right here, that's at like about -5. And when time we get here, which is a full decade, we're at -25. Same deal. The same information I just drew on the other one, but just nicer. Okay. That's a first order Bode asymptote. Next week, we will start off by talking about second order Bode asymptotes. And that's going to be a little bit different. There's, as you guys probably guessed, since there were major differences between first and second order systems in time domain, there are also major differences between first and second order differences in the frequency domain. Okay. Do you guys have any questions on asymptotes so far? I got one more thing to show you. So this is great. We can draw them, right? But Dr. D, have you ever heard of MATLAB? Yes, I have. Thank you for asking. It's a great program. It turns out that MATLAB will do this for you. Right? So if you want a Bode diagram, you create an LTI system, right? So you create the transfer function like we've done in the past. Use the TF command, right? And you set up your numerator and your denominator coefficients, and then you use the command Bode, and Bode will return this. And this is the same example that we just did the by hand Bode plot for. Right here. Look, the asymptotes still are holding, right? Look. Most easily notable, right? 1, 2, 3, 4. As you can tell where the corner frequency is, right? And again, you'll have something like that. It is very nice to be able to draw these from looking at a single transfer function. It's nice to understand what you should be getting out, because when you actually get one out of MATLAB and you know you have a first order system, right, you should know that it should look something like this, right? Second order systems, we'll talk about that next week. There's a little bit more to it, but the same general principles, right? Okay. Any questions on this? So how do we use a Bode diagram, right? It's great that we can draw them. It's great that MATLAB can give it to me, right? But how do I actually, why is it useful? Okay, well, say somebody gives you a Bode diagram and tells you, I don't know, that you have an input that's like 7 sine of 2t, right? Let's just pretend that that's a thing that somebody would do. Well, and then they ask you, hey, can you get me that steady state response for this system, given this input? And you say, yeah, sure. Right? And you don't need to know what the transfer function is to do it, because you have the Bode diagram. So what do? You come over to 2 radians per second, where this purple line is, right? And I look at my Bode diagram and I say, well, this has a magnitude of 2.5527 here. What if you didn't have like a way of being super accurate like that? Right? What if this was like just a piece of paper that someone handed you? Right? Well, you would look at that and I would hope that you would say, that's roughly 2.5. Right? Rough estimate. It's about 2.5. Okay, but that's great, but that's in decibels, right? That's in decibels. So what do we need? We need to get this in not decibels, right? Because remember, the equation that we're always trying to satisfy for steady state in its general form looks like this, right? That's what the equation looks like. And yes, you know what the transfer function is, right? But let's assume that we didn't know what the transfer function was, right? All you were given was the Bode diagram. I know that G of j omega in dB is 2.5527. This should be equal to 20 times the log of g of j omega, right? The original magnitude. I want the original magnitude because I need to take this and I need to put it into this equation. So how do I do that? Well, I'm going to algebra this, right? Well, first thing I have to do is divide by 20, right? Times log of g of j omega. And then I have to raise it, take everything to the 10. So raise everything, or I have to give everything a 10 to the power of whatever, right? And raise everything to that power because log is base 10. And if I do that, I'm left with this equation here, right? So if I want to convert back, if I want to convert from decibel back to unitless, it's 10 to the g of j omega in decibels divided by 20. That's what it is. And we get 1.3416, right? So this is 1.3146. Oh, no, thank you. Times 7, right? Because U naught was 7. Times sine of 2t, because we know that the frequency was 2 radians per second. And now we just need phi, right? Well, we come here, right? We pull phi from right there, right? Off my phase. That tells me that it's negative 26.57 degrees. I convert it to radians. Minus 0.464, right? So that's how we get here. So if you're given a Bode diagram and you're told what the input is, you can determine steady state, right? You can determine what steady state is. What if you're given a Bode diagram and not told what the input is? Then you can't determine steady state because you don't have enough information. You need to know what the input is. What if you have a range of frequencies for a specific input that you need to operate over? And you can test steady state for a range of frequencies, right? You can figure it all out. The thing about this system is, right, when you look at the other thing that you should be comfortable with Bode plots is when you look at this, right, when you look at this first part here, right, from here until we cross 0, right, is all amplification of my sine wave. For frequencies between 0.1 and what's this, 4, 5, and about 6 radians per second, you are going to amplify your signal. You are actually going to get more amplitude out. Once we start crossing 0, right, so anything above 0 is amplification. Anything below 0 is attenuation. The systems that we were using earlier, when we went into simulate, when we had smaller amplitudes coming out, those were all attenuating, right? Something that attenuates high frequency vibrations is also known as a low pass filter. Because essentially, the dynamics of this system are such that it filters out any high frequency vibrations. Now, is this a common thing? Lab 2, you guys applied a sinusoidal input to the electromechanical system. Did you have more or less movement on the final part than what you put in? Less, because you filtered out all of that stuff through the natural dynamics of the system. Your car's suspension is built to work this way. Every little bump on the road is not something that you feel. Asphalt is not smooth, but when you're driving in your car, you don't notice every little imperfection in it. What you do notice are the big one-off potholes and speed bumps, which are low frequency, super low frequency. Okay? We're not going to do this one today. I don't think we have enough time. Plus, I didn't do it with the other class, so I'd rather keep you guys all at the same spot. So thus we will end today's lecture. You guys have any questions? That stuff. Next class, we'll get into second order Bode system, Bode plots, bandwidth, a bunch of other cool stuff. We'll watch some videos, right? We'll do the things. But for now, this is done. Have a good weekend, everybody. Remember, I have office hours tomorrow from 3 to 5. Tomorrow from 3 to 5. As usual, when you're filling this out, if you are in the lower half, I would really recommend that you come to office hours and talk to me about what's going on so we can try to get you straightened out before the next 2 weeks, before we have to take another test, right? All right, and then the confusing thing. We'll do more examples next class. We'll go through the second order systems and we'll probably hit transmissibility next class. Take it easy.